Hi everybody. In this video I want to draw some analogies between operations between vectors in ordinary three-dimensional vector space, like in introductory physics, and operations between functions in our infinite square well function space defined from x equals 0 to x equals a. And we'll go even further and draw some analogies to operations between states in some abstract quantum state space, represented in Dirac notation. All right, here we go. So in three-dimensional ordinary vector space, there's something known as the dot product. The dot product of vector A and vector B is equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine of the angle between those two vectors. It turns out that the dot product that we know and love from introductory physics is an example of something known as an inner product. An inner product is a more general mathematical term. The inner product in our infinite square well function space, it turns out, can be constructed as follows. Let's say we have function f and function g, and these are in our infinite square well function space defined from x equals 0 to x equals a. We can construct the inner product of those two functions as follows. Take the complex conjugate of function f, multiply by function g, and integrate from x equals 0 to x equals a. All right, so this is an inner product in our infinite square well function space. More generally, we can represent that more abstractly, in our with Dirac notation. We can imagine some quantum state f, some other quantum state g. We can take the inner product of those quantum states. We represent that with this bracket. All right, so this is an abstract representation of this, or it could be a generalization to other types of quantum states as well. Okay, so inner products. The dot product is an example of an inner product, and integrals of this type, which we've already been doing, is another example of an inner product specific to our infinite square well function space. All right, so let's move to the topic of normalization. Now, in our ordinary three-dimensional vector space, a simple example of normalization is this. X hat dot x hat is equal to 1. So x hat's a unit vector. The dot product of x hat with itself will give you 1. So we would say that the unit vector x hat is normalized in this ordinary three-dimensional vector space. Likewise, y hat and z hat are also normalized. In fact, any unit vector in our three-dimensional ordinary vector space is normalized. Okay, what does normalization look like in our infinite square well function space from x equals 0 to x equals a? Well, we would say that the function f is normalized if we take f star, multiply it by f, if we integrate that from 0 to a and get 1, then we would say that f is normalized. Abstractly, we can represent that in Dirac notation as follows. A state is normalized if when you take the inner product of that state with itself, you get 1. That means that state is normalized. So this is the normalization condition, generally speaking in Dirac notation. This is the normalization condition for functions explicitly written out for infinite square well function space. This is an example of normalization for ordinary three-dimensional vectors. All right. Next topic, orthogonality. In ordinary three-dimensional vector space, orthogonality just means perpendicular. So the x direction is perpendicular to the y direction. So x hat dot y hat gives you 0. Why does that work out? There's a 90-degree angle between the x direction and the y direction. When you put the 90-degree angle here and use the formula, you get 0 for the dot product. So we could say that in three-dimensional ordinary vector space, two vectors are orthogonal if their dot product is 0. But dot product is an example of an inner product. So let's use that language. If the inner product of two vectors is 0, those two vectors are orthogonal. Well, maybe we can define something similar for functions. In fact, we can. In infinite square well function space, defined on the interval from x equals 0 to x equals a, we would say that function f and function g are orthogonal if their inner product is 0. Well, here is how you construct the inner product of f and g, right? The inner product of f and g is just take the complex conjugate of f, multiplied by g, integrate from x equals 0 to x equals a. If that inner product comes out to 0, then f and g are orthogonal. So this is the orthogonality condition explicitly written out for infinite square well function space. We could write that more abstractly in Dirac notation using abstract quantum states. This is just our abstract notation for inner products. Here's the inner product of f and g. If that comes out to 0, then state f and state g are orthogonal. So this is the orthogonality written out abstractly. All right, with normalization and orthogonality, this is a good time to talk about an orthonormal basis.